Okay, so today what we're gonna do is just discuss in some problems. So every year I would normally give some problems in the lab, and not everything has to be taught. Given the time, I'll have to just discuss it around as theory over here. So let's start off with the first. So this one is, of course, a very simple program. Looking at the problems given for the lab as exercises, you may have already solved it up. So it's a grid. I need to go from a source to goal, and there are, of course, some obstacles around it. The actions have cost, so this is 1, this is 1, this is 1, the diagonals may be root 2. Now what I say is that instead of going to the goal, you need to go at these special places. So they may be treasures, they may be some interesting landmarks, and you just need to go to one of them. So you either need to go to, that's your source, G1 or G2 or G3 or G4 or G5. So of course your state happens to be XY. Your actions happen to be up, down, right, left, and depending upon whether you model the diagonal or not, nothing really changes. Your feasibility functions remain as it is. Your action costs are still 1, 1 and root 2. How do we really go upon writing down the heuristic functions of it? Now, the relaxed problem is, of course, do not consider the obstacles, so everything is reachable by straight lines. And because everything is reachable by straight lines, my heuristic function is just going to the closest goal. So it's a distance between S and GI, and I will find the closest goal, or the one which has the minimum distance. If you only have up, down, right, left, you will probably consider the Manhattan distance. And if you have the up, down, right, left and the diagonals, you'll probably consider the Euclidean distance. If you see a long fancy term, then that is also correct, because even in case of diagonal, you can only move at 45 degrees. I can calculate a much tighter heuristic, more informed heuristic in such a case. So that's an interesting little problem. Sometimes what I might do is that instead of saying that you need to go to the closest treasure, the closest food, I might say that you need to go to the closest two of them. So let's say it is G2 and G4. So from source, you need to go to a G2, then you need to go to a G4, and this could be any. And this again could be any. Now you see that my decision making, it also is affected by what all goals have I achieved in the past. If I have not achieved any goal, then I need to go to 2 goals. If on the other hand, I have achieved at least 1 goal, then I just need to go on 1 goal. So your state over here, so if I model this problem like this, my state is not only my XY location, it is also, have I achieved G1 in the past, have I achieved G2 in the past, have I achieved G3 in the past, have I achieved G4 in the past, have I achieved G5 in the past. It's also this bitmap which tells me what all states have I achieved in the past. My goal condition is 2 of these need to be positive. So that's my goal criterion. Like here, the goal criterion was that I should be standing on a grid value which is a classified goal. Here, 2 of these need to be positive, and the moment I land on a goal in that particular state, I make that to be positive. the heuristic function. So it's not xy, it's the state S. So the heuristic function, you'll get two options. One is that no goal achieved so far, and the other one is, of course, for this specific case, one goal achieved so far. You cannot have two goals achieved so far, because the moment two goals are achieved so far, it's a goal state, and you will directly put the value of 0. That's a valid goal state, so that heuristic value is 0. If one goal has already been achieved, then you go on to the previous heuristic function. It's all about getting one goal out of multiple options, only considering the goal which have not been achieved. So it is the minimum, the distance between S and GI, of course for all I, such that GI is false in the state. So let's say in the state GI is false. And if no goal has been achieved so far, then it's a more interesting. That means from source you need to go at some GI which has not yet been achieved, and then you need to go at some GJ which has not yet been achieved. So you'll minimize the distance between S to GI plus distance between GI to GJ, and you need to minimize over all combination of I and J. I not equal to J, and of course GI is false in the state, and in the state GJ is also false. So that's the one that goes around over here. I need to achieve any two goals. It's more interesting if it's a traveling salesman problem. I need to achieve all the goals which are possible. So the state representation remains the same, that what all goals have I achieved in the past. The heuristic is more involved, because as I increase these loops, now remember my heuristic function is what is taking a whole lot of a time. If you want to be specific, then of course the minimum spanning tree is the heuristic function for the traveling salesman problem. That's more involved. So if I need to achieve G1, G2, G3, G4, G5, all of them, then I'll probably use something like that. If I need to go in a sequence, that means that I have two goals, G1 and G2. I first need to go from source compulsorily to G1 and then compulsorily to G2. These are some, of course, interesting problem that if I have to go to my lab, first I need to go to where the key is placed and then solve that up. You can actually solve these problems independently. There's no need for a joint operation. So your state could be just XY. First get this part, then get this part, and join the two of them, and you've got your part. Some cases I'll let you decide. It will not be possible to break this up. So I say that there's an orientation. I could go to G1, but I could be at any one of the four orientation. And the orientation here is important for what is the orientation there. So in that case, it cannot be broken up. Now, these are not only for the grid problem. I could do that for the 8 puzzle as well. So over here, I could say that there are 5 winning combinations. You go to any one of those 5s. Absolutely possible. I could also say out of 5, you need to touch 2 winning combinations. So why 1, 2, 3, 4, 5, 6, 7, 8, minus 1? Why not 8, 7, 6, 5, 4, 3, 2, 1, minus 1? It'll look like an inverted 1. It'll still look similar picture. People will love it. So it could be done in that way and in that manner possible as well. So talking about orientation, that's again a very popular question. So I say again exactly the same grid map. So nothing really changes in the grid, it remains the same. But what I say is that I can only move forward. So my only action is forward, which has a cost of +1. However, I can also turn either a 90-degree clockwise, or I can turn a minus 90-degree clockwise, which is 90-degree clockwise, and the step costs are again +1. So now that's interesting. It may appear that xy is the state, and people think about, okay, now how do I apply the action? How? What's plus 90 degree? You remain at bloody the same xy. So, I mean, of course, the answer is that you've got the xy and theta, where theta could be either 0, 90, minus 90, or 180. So, this is 0, this is 90, this is minus 90, and this is 180. And depending upon that, you only move forward. So just a case, if I need to move from this source to this goal, my actions will be forward, forward. So from here to here forward, from here to here forward, then turn 90, which is here, then forward, then forward. So forward, forward, turn 90, forward, forward. If I still need to go here, turn 90, forward, forward. If I'm looking at here, I need to go here, it's turn 90, forward. So that's how it goes. So my state in this case, the angle cannot be abstracted out. I need to consider the angle as well, because my actions are dependent and my action costs are dependent upon where am I actually looking at. And because of that, again, it becomes interesting that what really is my heuristic function in such a case. One way is that you say that eventually I'll travel the Manhattan distance. So it will be nothing but in my state the x value minus goal state the x value plus in my state the y value minus goal state the y value, or the Manhattan distance. That's absolutely correct. There's nothing wrong in doing that. But what you could also consider is use the angle information. And the angle information is if you are facing towards the goal, if the goal is right ahead of you, which means you are facing the x-axis and the goal is right in front of you in the x-axis, then the extra turn becomes 0. If you're facing the y-axis, goal is positive in the y-axis. If you're facing the y-axis, goal from below, goal is negative in the y-axis. Then you take the turn factor as 0 if robot is facing goal. On the other hand, if the goal is not in the same axis, the goal is somewhere else, and you are either facing it in either of the lines, then you need to take a 90-degree turn in a way, so the turn factor will become +1. On the other hand, if you have goal in line, but you are 180-degree turning away, then you'll have 2 as the goal turn factor. And similarly, if you have the goal in any one of the quadrant, but you are not facing that quadrant, then you'll have to make an additional turn. So this will uplift the heuristic value just a little bit, based on which you may get the result just a little bit earlier, by looking at not the quadrant, because there are 8 options possible. Either is the goal in either of the 4 axes with respect to where the robot is facing, or is it in the 4 quadrants? So you'll get in those 8 cases, and depending upon those 8 cases, you can either add 0, 1 or a +2 as the turn factor. Now, that's to do with when I say that the orientation is important. The first time I gave this thing as a question, I think the entire class got it wrong and I was surprised. And people were asking me the same question. So XY is the state. There are 3 actions possible, but how do I do that? Yes, your state is wrong. People still make that mistake, by the way. So let's go on to exactly the same question. So I've got a simple grid like this, some obstacle, I'm on a source, and instead of saying that every step has one cost, I say some of these are slippery, some of these are sandy, some of these have things on which you will have to step. So there's a cost in going from any state to a XY, depending upon what is there. Some may have broken glass, your foot will pain. And even if you need to solve that up, then of course you need to just use Dijkstra's uniform cost search or the A-star algorithm, of course. The state will remain XY, the actions will remain up, down, right, left, maybe the diagonals, how you model it up, and your step cost will now be given as a cost where you land. So, and exactly the same. So the cost in going from CSAS dash is basically sometimes one additional, sometimes not additional. So let's call it as, there cannot be two C's. So let's call it as G. So G of S dash dot X and S dash dot Y. Now, something what I'll say is that I'll say the agent can make a jump. So from here you can go here. You can make one jump of 2 units. And the only problem is you can only make jump once in your entire lifetime. Now, have I made a jump in the past or not? That's also important for decision making. So my state, it actually becomes XY. Did I make a jump in the past, or the number of jumps that I have made in the past? Now that's important because my actions are 4 if I have, or 8 if I have not made a jump. On the other hand, my actions are exactly the double in which direction do I make a jump if I have made a jump in the past. And you do not know, there's no heuristic about when to make a jump. So that is what your state becomes. The action will of course be just up, down, right, left. Let's only consider 4. If jump is equal to true, that means if I've already made the jump, and if jump is equal to false, then I not only have up, down, right, left, I also have jump up, jump down, jump right, and jump left. So that's how I decide. Sometimes I may say that in the same question, you need to reach within time t. Now remember, now there's a cost to go from source to goal. It's not the same as time. So you can only make 10 moves possible. So now my state becomes XY as well as the time. Okay, by the way, the heuristic function for this problem, I should have discussed it before. Without the jump is, you calculate which is the least navigation cost, and you assume the entire grid has the same navigation cost, the least of all the grids, and then you go upon doing it. Similarly, over here, the heuristic for function, it now depends upon the jump. If you have not taken the jump so far, so it's the same cost, relaxed problem. Just take one jump immediately and then calculate the cost to goal. If you have already taken the jump, it's just the Manhattan distance time, the least cost. Talking about here, so I need to go from a source all the way up to the goal. And the problem is that now the cost and time are two different things. You may have a very long path which has the least cost because you're going through things which are safe. You're not taking those glass and those slippery floors. You're taking proper roads. However, I need to reach within a time t. That means Sometimes I will have to take the risky routes which have a high cost. My legs will pain, glass may go inside my leg, but I'll have to take it as per constraints. State is x, y, and time. So now it's a three-dimensional where time is another axis. And time decides what action I do. And of course, similarly for the heuristic function, you can relax that up. Let's take in same grid problem, same state. So I say that there is a person who is going like this, and the trajectory of the person is exactly no. And because the trajectory of the person is exactly known, therefore, even though your map is changing with time, but the changes in the map are known well in advance, again the state happens to be x, y, and time alone. Why time is important here? Because time decides what the map is. The map is changing with time. Time decides what the map is. So my state is x, y, as well as a time. The actions are common. So it's again three-dimensional in nature. The only thing which will change is feasibility action functions. And in feasibility action, what will happen is that you'll take the latest time, and after taking the latest time, you'll take the current time of the current state. After that, you will take the map at that time, and after taking map at that time, you will check what you really need to do. What's the cost? What's the feasibility? So let's do that. My actions are up, down, left, right, and a special action which is called as no action. In these problems which are time varying, sometimes just sitting at your own place for 1 unit, for 2 units of time is good. Map will become more favorable. As in, you are here, all these are obstacle. Now the only thing you can do is follow this person till he leaves the goal. So you will have to wait, step. So that's your no action. It's called as no operation. It's important now because your time is a factor. Even if you don't apply an action, x doesn't change, y doesn't change, but time does change. So taking no action makes a lot of sense. Other cases, of course, if you read any general book, a no operation action is always modeled. We did not do it. We absolutely did not do it because of the fact that the state will have come exactly the same. But here, even though x, y don't change, by no operation, the time changes. And because of that, now you need to take the no operation action as well. And this will be applied to a standard 8 puzzle problem as well. I say some pieces are heavy, some are light. So every piece is made with a different metal, and you need to solve it in exactly maximum 10 moves. So you'll have to move the harder ones as well. So the heavier pieces will also have to be moved. Otherwise you could try moving more the lighter ones, but now there's a restriction that maximum time is fixed. To my favorite, so in multiple agents, we talked about competitive. Did we really talk about cooperative? No. And do I really need to do? So classic problem. You've got the same grid over here. You've got two people, the person A and the person B. All you have to do is you've got to make these two people meet anywhere. And of course it's a cost map, so every grid has a specific value. So if I move from here to here, I need to invest a cost of 3. If I move from here to here, I need to invest a cost of 2. If I move from here to here, this is glass, your legs will pain. 9, this is slippery, so it's heavy risk. So cost is 8. So I need to make them move anywhere. So what's changing in the system? A's position is changing and B's position is changing. And that's exactly what is my state. What are my actions? Both could go up. A could go up. B could go down. A could go up. B could go left, and so on. Now there's a general way of writing it up, and that's exactly what are cooperative agents, and that's exactly how it's a join. We say the state of a cooperative system is the state of the first system joined to the state of the second system, state of the first system joined to the state of the second system, joined to the state of the third system, and so on. And in terms of actions, we say it is actions of the first system, including the no operations, times actions of the second system, including no operations, times the actions of the third system, so on. If you want, you can, for this particular case, subtract one specific action from the cross product when nobody moves. Everybody is static. That will give you exactly the same state. Nothing will change. So in a cooperative modeling, in a cooperative system, the state is a join of all states. The action is a cross product of all actions. And because we are not doing the generic case, we are doing a specific case over here. So let me complete the actions notated as a cross product rather than everything up. So my actions are up, down, right, left, no operation, cross, up, down, right, left, no operation, minus no operation specific case. So that says up, 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 down, up, left, up, right, up, no action, down, up, down, 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 left, down, right, down, no action, left, up, left, down, left, 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 right, left, no action up, no action down, no action right, no action left, no action, which will get us subtracted, of course, over here. The feasible actions are when both the actions are feasible. The A's action applied to XAY is also feasible, and B's action applied to XBYB is also feasible. For the H puzzle, of course, the one that I gave previously was there are two hands, and you can simultaneously move two pieces. The only thing you need to care about over here as well as there is that many people model this also as feasible. It's not possible, A and B swapping places. So that needs to be swapped. Similarly, for the 8 puzzle, you've got 2 blanks instead of 1. It's not 8 puzzle, by the way, then it's a larger puzzle. You've got 2 blanks. Both operating on the same blank is also not possible. Both operating on the same piece is also not possible. One moving it left, the other moving it on right. And the last one that, of course, I will take in, another simple one. So in the same grid, I say you don't need to go near it, so you need to maintain some distance from it. You don't need to go it. That is what you can clearly do, either offline, so say anything neighboring obstacle is also an obstacle, and use the modified map. Or you could change your feasibility to say that any state S, if it's neighboring to an obstacle, is called as infeasible. So you basically leave, practically you leave some contingency, you don't kiss the obstacle, you leave some comfortable distance from the obstacle. That is what it does model. So my again mantra would be that try to code in as many problems as possible. This is the first time I cannot give all these interesting problems in the lab. Otherwise, these problems will never come in theory, they'll only come in lab, and only in lab people will find out these problems, they'll try to solve that up, and they'll see that if they can really solve this thing up or not. Just because I've changed my strategy and I've given some hints along with problem definitions, and there are no marks for really solving these problems this time, doesn't mean that you don't practice it yourself. Practice all these problems yourself, take all the tips and tricks that you can. By the end of it, I do expect that you have one thing clarified, which is about how to make a heuristic function for all these problems. What happens if there are multiple goals, you need to do something, you need to do something else. So the most important part of research is, in order to make a heuristic function, if you can do that, then there's no way you cannot not solve any problem. The algorithm will remain exactly the same, the implementation will remain exactly the same. What will change is what is the heuristic function. And because of my bad experience at this university with students, do ensure that you have the correct state. Otherwise, given a grade, people are like, this is XY. No. It could be XY for both the agents. It could be XY time. It could be XY orientation. It could be XY which of the goals have previously visited or not. And it's not only for the grid, for the 8 puzzle, for missionaries and cannibals, for any one of these I could make the state unobvious, where I gave you some extra information and that does affect your decision making, so it has to come inside the state. Time, one action only allowed one time. So all those information, because they do affect your state, it has to be inside the state vector. Now, a trick, of course, is that many people have followed. Whenever in doubt, keep things in the state vector. Graph search does not have a major dominance as compared to tree. So putting things extra into the state vector, the only thing that changes in the algorithm is you'll not be able to prune states as a graph search because the extra information might not match. So whenever in doubt, put any information that you like and solve that up. At least you'll get a correct answer rather than missing out on something which should be in the state vector and is not the state vector. And above all, of course, keep practicing that up. These are new topics which can be extremely difficult from an applied perspective. The more you solve that up, the more informed and the more intelligent you become. So it's all about taking a theory class. It's all about whether you can really appreciate when, what it's changing and how. So I'll end up with this. Thank you so much.